scientists and space enthusiasts out there, and welcome to the Mad Science event, Seeing Starlight with the James Webb Space Telescope. So we are going to get started very soon, and we have an out of this world fun hour planned for you. First things first, my name is Jupiter Jen, as you can see on the screen, and I'm a mad scientist. Now, I may be an expert in cheesy space jokes, and I know some interesting space facts, but I am very pleased to tell you that we have an expert here with us today. We have Dr. Hart, who is an astrophysicist and a senior education and outreach scientist at the Space Telescope Science Institute. So she's waving at all of you. Give her a wave, tell her hi. So she'll be back soon, and she will help us learn all about the life cycle of stars. She'll share details about the Webb Space Telescope, including the technology used, what information can be collected, and what we can learn from this information. Towards the end, Dr. Hart will be answering your questions. Now, we collected over 100 questions from the registration page, and we'll answer a few of the most popular questions. We hope to answer all of them, but I don't think it's possible to answer all of them. And we also hope that we can answer some live questions as well. And don't forget to stick around until the very end, since we're doing a prize giveaway for 4 lucky winners of our Loop Lab subscription box. And I cannot wait to give those prizes away, so please stick around. Now we have some technical questions. I have some technical information to give you, some quick technical tips to start. If you're having any issues hearing us or seeing us, we recommend that you try joining from another device if you have one handy. I see some hands raised. We can't answer all of the hand raised questions, but you can type in your questions into the chat for right now. This virtual meeting might be a bit different than the ones you're used to. Everyone is muted. That might be one of your questions. Hey, how come I can't say anything? We want to be able to hear our guest speaker, so everyone's muted. If you have a question that we're able to answer live, we'll ask you to unmute, and then you can let us know your question. As well, because there are so many kids who've joined us today, we only have space for a few cameras to be on. So if you can't see yourself, that's okay, as long as you can see and hear us. We also have a Q&A section at the bottom of your screen. Like I said, for those of you with your cameras off, you can message us with any feedback, questions. You can say hi. We have a team of mad scientists to get through as many as we can. Now, one of my favorite questions to answer is, what is mad science? I bet a lot of you already know mad science from your local communities, but what you might not know is that we are the world's leading science enrichment provider for kids aged 3 to 12. Are you between the ages of 3 and 12? Give me a thumbs up if you're between the ages of 3 and 12. Okay, good. We got a good crowd with us. So we have a global reach of 150 locations in over 20 countries and counting. Today in this virtual event, we have over 25 countries represented from all over the world. We're kind of like the Science Olympics. I like to call them Science Olympics. It's my little shortened version. Some of these countries include USA. If you hear your country, you can give us a little whoop whoop. So we have USA on the call. We have Canada on the call. We have the Philippines on the call. We have Turkey. We have India. We have the United Kingdom. So give a wave to everybody out there. And if you didn't hear your country called, you can definitely tell us where you're from in the Q&A. We'd love to hear it. We absolutely, at Mad Science, we love bringing science, fun and educational science programs to kids. We do birthday parties, after school programs, summer camps, workshops, and virtual events just like this one. So the fun does not have to stop here. Be sure to look for a Mad Science location near you. We also want to tell you about our very special mission, because it has to do with kids just like you. We are on a mission to spark the imagination and curiosity of children by providing you with fun, interactive, and educational programs that help you learn more about science and how it affects your world. So I'm assuming that because you guys are on the call, that you all love science. So show me a heart if you love science. Yay, that's great. We also get to work with some amazing groups of people. So for today's project, we work with 2 teams of very special people. Now we're going to show you the logos of some of these groups. Hopefully we can get those logos on the screen. We were excited to work with the National Institute of Aerospace. So our friends at NIA create videos and activities that are not only fun, but help you think and act like scientists and engineers. And they worked with us to develop the fun bracelet activity you'll do today, and that's coming up in just a few minutes. We were also grateful to work with researchers at NASA's Goddard Space Flight Center who worked on the Webb Space Telescope mission. So these friends helped us make sure that the science that we're sharing with you today in the bracelet activity is accurate. Science is the study of the world around us here on Earth and in space. So our understanding of that science may change as we're able to use better and better tools and equipment. And that's why we are very excited for the Webb telescope to launch in 2021. So this new tool is going to help us learn more and more about space. Okay, so that's it for my little speech. We can stop sharing the screen with the logos. Is everybody ready to make this bracelet that you see on my wrist? If you don't have all the supplies, that's okay. But we're gonna start our event by making a star life cycle bracelet. Now you may be saying, Jupiter Jen, that's a bracelet. What does that have to do with space? What does that have to do with astrophysics? Well, have I got some interesting news for you? This bracelet contains a very special color code that helps us learn about the different stages of a star's life cycle. So in order to get ready for Dr. Hart, who we saw before, I'm going to show you how to make this special bracelet. I'm going to show you a little close-up video, and we'll keep it handy. We'll keep our bracelet handy so you can follow along when we learn about the different stages of a star's life cycle later on in the show. Now, I want you guys to listen to me very carefully. I might go a little quickly to make sure that we have all the time for the fun stuff we have planned. If you need more time to make your bracelet, if you don't have all the supplies, if you need help to tie the knots, if you're not making it at the same speed as me, I don't want you to worry. It is a-okay. We have an instruction booklet that we sent your grown-ups that you could look at after the event, or you can look out for this video on our YouTube page, and we'll be posting it in a few days, and you can replay the instructions as many times as you like. So here we go. I'm going to start by sharing a video of how to make this bracelet. Is everyone ready to make their bracelet? You might have plastic beads, you might have paper beads. I see a couple of people give their thumbs down. That's okay. If you don't have the supplies, no problem. Oh, look, I see Olivia the astronomer has already made her bracelet. Ooh, la la, that's really nice. Okay, so if you're ready to make your bracelet, show me your wrists. They're all ready, they're all prepped. See some thumbs up. So I'm going to share my screen, and we are going to play some fun videos for you. Okay, so the first step is to take your string, and you're going to wrap the string 3 times around your wrist. So I'm going to play a video here. Hopefully you guys can all see it. You're going to wrap the string around your wrist 3 times, and this is to make sure that the string is the right size for your wrist. And you can ask a grown-up to help you cut it at the correct length. You want to make sure you're safe with the scissors. Make sure you're pointing it away from your skin, away from your face. So I see some people have helpers. So I'll play it one more time. You're going to wrap the string 3 times around your wrist to make sure it's the right length. Wow, what a beautiful wrist that is. It's my wrist. Okay, so we're going to move on to the next step. And for this next step, you're going to need your green bead. So hopefully you all have your green beads. If you made paper beads at home, this is the 0 paper bead. It's called the star forming nebula. So what you're going to do is you're going to take your green bead and you're going to slip it onto the string that you just cut that fit around your wrist. And you're going to put it in the center of your string. And then what you're going to do is you're going to tie a knot around that bead. See, it looks like a pretzel. It's getting smaller and smaller and smaller. And there we made our knot around the center green bead. So that was one of the easier steps that we have. So we just have a knot in the middle of the green bead. I will move on to the next step. So once again, if this is going too fast, don't worry. We have this recorded and you can refer to it later. I just want to make sure we keep a good pace so we can get to Dr. Hart and all her fun information. Okay, so now we're going to start our sun-like star life cycle. So for this, you're going to need your blue bead, your yellow bead, your red bead, your orange bead, and your white bead in that order. And I'm going to press play. I have a little chart here for you if you're using paper beads. Make sure you do it in the same order as I have it here. And once again, Dr. Hart's going to tell you all about these special colors. So you have blue, you have yellow, you have red, you have orange, and you have white. So now we're kind of halfway done. So I'll pause it here, just give you guys a little bit of time. So your bracelet should now look like this. You have a green bead in the center and you want to push your blue, yellow, red, orange, and white bead as close to the green bead as you can so it doesn't fall. So now I'm going to go to the next slide. Once again, don't worry if you're not as quick as me. I've made this a few times, so I might be a little quicker than you guys. So now we're going to start our massive star life cycle end of the bracelet. So what you're going to do is you're going to take a blue bead, a yellow bead, a red bead, a purple bead, and a black bead. And you're going to thread it on the other side of the green bead. And make sure you're doing it in the same order as me. You have blue, then yellow, then red, then purple, and finally we have black. I wonder if some of you can guess what the black bead represents. So here you have your bead. Your beads are all on right now. We just have a few more steps before we can finish. So I'll go on to the next slide. So now what we're going to do is we're going to make our string into 2 loops. So this step is the trickiest step, I will warn you. So you might need some grown-up help for this. What I'm doing here is I'm just putting tape around the end so that it'll help me push the string through the green bead. So you're going to take one end of your string and put it through the center green bead. Push, push, push. It might be a bit hard because we're running out of space in the center of the green bead. And you're going to end up with a loop. Then you're going to take the other end of the string and you're going to push it through the green bead. Push, push, push. There's not a lot of space left, but I know you could do it. And you're going to end up with something that looks like an upside down bow with 2 loops like this. And then the second last step is we want to make sure your loops fit your wrist. So this is a quick step. You just put your wrist inside the loops and make sure that they're fitting. So you can adjust them very, very easily. You just pull on the ends. You see my loops were a little bit small. I'm making them bigger. Like that. So now you end up with a bow, but it looks a little bit different. It's not an upside down bow. It's kind of like a bow with 2 strings at the top and the bottom. And then the final step is to make sure your beads don't fall off. So what we're going to do is we're going to tie a knot around the green bead. And then we're going to tie another knot just to make sure that our beads don't fall off. And now that I've tied my double knot, my beads are not going to fall off. So I know that that went really, really quickly. Once again, you can refer to this video after. We want to make sure that you're learning all the good stuff from Dr. Hart. So we want to save enough time for that coming up. So some of you may have completed your bracelet, some of you might not have. That's okay. You can still follow along the presentation. And is everyone ready now? You can see my thumbs up. It's a smiling hand over there. Is everyone ready to welcome Dr. Hart to the presentation? Yes, thumbs up, thumbs up, thumbs up. Everybody thumbs up. Okay, so welcome Dr. Hart. Thank you for being with us today.
Hi, everyone. How's everyone doing? You having a good morning, afternoon, wherever you are? Thumbs up. I'm looking off to the side because your videos are on my other computer here. I'm so excited to be here with you today. And let me test something real fast. I'm going to share my screen, and Mad Science can tell me if they're seeing what I think they should be seeing.
It looks great, Dr. Hart.
Great, great. So welcome everybody. I'm so happy to be here with you this morning to share with you a little bit about the star life cycle and the James Webb Space Telescope. So my name is Dr. Quyen Hart. I'm an astrophysicist and a senior education and outreach scientist. I work at the Space Telescope Science Institute in Baltimore, Maryland. We are the Science Operations Center for the Hubble Space Telescope, and we will be the Mission and Science Operations Center for the upcoming James Webb Space Telescope. So let's get right to it. Now we're talking about life cycles. Now I want you to write in the chat, do you know any examples of life cycles on Earth? So I think I could see the chat here. So go ahead, just drop in your answers. What other kind of life cycles do you know about around your community, in your backyard, at the park, at school? So what do I see? I see Jefferson saying bird. Oh, no, it's more. Butterflies. Angela, puppies. Mason, frog life cycle. These are great. These are the ones that, where's my cursor? These are the ones I also thought about. So for example, you can think about a butterfly. It starts off as an egg, becomes a caterpillar, then it becomes a chrysalis, and then it emerges as a butterfly. And then those butterflies lay eggs and the cycle begins again. And we could say the same thing for frogs. Frogs lay eggs, and then there's an embryo, it becomes a tadpole, it has 2 legs, then 4 legs, then a young frog, then an adult frog, and the cycle begins again. Now, some of you might have thought about the water cycle. So water on Earth, whether it's from the streams or the land or plants, evaporates, it turns into a gas, and it goes up into the sky, and then it can create clouds. And sometimes those water vapor can get heavier as it collects in those clouds, and eventually that falls down as rain. And then the rain here can go on the hillsides and drain into your streams, go into the groundwater, and then the cycle begins again. So you guys are familiar with life cycles. So now I want to talk about the life cycle of stars. So I have my life cycle, but I made a necklace here. Okay, so my green bead is on the back of me here. So it's right here, green, I think. And then I have my 2 cycles. So some of you said, I don't have colored beads. Well, maybe you have construction paper at home. Or maybe you just have white paper and you have crayons and markers. So you can do this in any way that you like. You can even make this really large and hang it on your wall or something like that. Be creative. That's the best thing about anything in life. So the handout that you got for this, there's a cycle for sun-like stars and there's a cycle for massive stars. So I wanted to give you guys some tools to remember all these different phases. So the first speed that you have, which is the green one here, right? It's at the beginning of each cycle. So green starts with a G. So let's talk about the gas clouds that can form stars. So these are star-forming nebulae. So this is a place where there's a lot of gas, okay, like hydrogen and a little bit of helium. But those are the building blocks to create stars. So you need that material to create them. So this is a picture in visible light of the Quyen Nebula. It's a star-forming region where hundreds of stars are being created. So Andrew from Texas and Amanda from California wanted to know, How are they created? Well, they're created in these places where there's a lot of gas clouds, and some places in those gas clouds are really, really cold. Now, the next bead here is blue. So on both cycles, you have a blue bead. So this blue here is about building up to be a star. So these are baby stars. They're protostars is the name that we use. So in these star forming regions, there are really denser places where a star is forming and it's collecting gas. So we have an example here in a kind of light called near infrared. It's called the bat shadow. So maybe see my cursor here, right? So there's a young star that's behind here. We can't see it, and there's material around it. It's actually creating a shadow that we can see. This is the Eagle Nebula, and at the tips of these really dense clouds are young embedded stars here. Now, the bat shadow is about 1,400 light years away from the Earth, and this picture on here is about 0.6 light years in expanse across here. All right, so the next bead color, so look at your bracelet. What's the next color you have here? And you can follow along on my little picture here. I'm circling the beads that you have already put onto your bracelet or maybe your necklace if you made one. So the next color is yellow. So everybody say with me, yay, I'm a star now, right? So this is when they're no longer baby stars. They're creating their own energy. So you know how your parents say, you know, one day you'll be old enough to do all the things that you want to do when you become an adult? Well, this is that stage for stars. It's the yay, I'm a star now, and I can create energy. And the energy is created on the inside of the star and it works its way out. So here's a picture of the sun taking an invisible light by the Solar Dynamics Observatory by NASA just yesterday. So this is a very recent image, and there are some spots on the sun here that you can see. Now, we're doing 2 cycles. So we have the massive star that's different than the sun. An example here is Spica. It's a massive bright star in the constellation of Virgo. So if you're in the Northern Hemisphere and you go out tonight around 8-ish o'clock, you'll see a very bright object in the west-southwest. Now that's Venus. But nearby in this region where you see this circle, that is Spica. Now you can find it. I know you can do it. So I want you guys to try this tonight if it's clear outside. So if you can find the Big Dipper, here is the Big Dipper. It's part of the constellation of Canis Major. So you find the handle here. So this is how you're going to find Spica. It's a really fun little saying. You arc to the star Arcturus, and then you keep on speeding on to Spica. So you guys can say it with me. You arc to Arcturus, and you speed on to Spica. And then that you'll know is a star, but it's not like the sun. It's more massive than the sun. So now the next bead that's on both bracelets is a red one. So this one is for the red giant or the red supergiant. So this red, you could say it with me, it's really fun. It's ridiculously large. So this is when the stars are no longer creating energy the way they were before in their cores, and they start to change. And really, there's a tug of war between gravity trying to push it in and pressure trying to push it out. And it's trying to get back to normal, but it can't quite. But it has to all do with the stuff in the center. So when the sun goes into this stage, it is going to puff up, okay? Kind of like this. Poof. Okay, so this red giant phase is not going to happen anytime soon. You don't have to worry about it. So about 7-8 billion years from now, it's going to puff up and it's going to swallow up Mercury and Venus. Eventually, it'll swallow up the Earth too, and it's going to get really hot. But again, you don't have to worry about it. The sun's going to live a long time. And so George from Great Britain and Kyle from Texas asked, when will the sun stop existing? What will happen when the sun dies? So it's around this stage where it's kind of doing things that it hasn't been doing for 10 billion years. And it's going to change for the next billion years or so. So we'll go through that next part of that life cycle. Now for the red supergiant, if you can find the star Betelgeuse in the constellation of Orion, that's a red supergiant, right? It is so big that telescopes can actually see the star Okay, we can actually see its surface there, which is the outer atmosphere. So the stars don't have surfaces because they're all made out of gas. But it's so big that if we put it in our solar system, it would be as big as all the way out to the orbit of Jupiter. So it's ridiculously large, right? Red, ridiculously large here for red giant or supergiant. Now, the next stage, we're only going to look at the sun-like cycle here. So you have an orange bead. That orange bead is for the planetary nebula phase, when the outer layers, O for orange, O for outer, the outer layers come off. Now, remember, I said there was a tug of war between the gravity trying to push it in and the pressure trying to push it out. And this is where the pressure wins. And it pushes the outer layers off, and the center of the star gets to be exposed. It's kind of uncovered, and it's really hot, and it heats up all the gas around it. So on the left here, you see the Helix Nebula. And all of this gas on the outside was the outer layers of the star, but pushed out into space. And this is a very, very short period of time for a planetary nebula. It's like a blink of an eye in a human life scale. Maybe tens of thousands of years it would be in this stage where we can see it. Here's another extremely beautiful planetary nebula called a Butterfly Nebula, because it looks like a butterfly. And they all come in different shapes and sizes. Just like everything on Earth is, not everybody looks the same. Well, not every planetary nebula looks the same either. Now, the Helix Nebula is about 650 light years away. And the extent, how wide this is about 5 light years. So a light year is how far you could go if you traveled at the speed of light. And you can't travel at the speed of light. Only light can. So one day, maybe you could, but right now we cannot. All right, so what's the next stage here? So look on that cycle. For the sun-like star, you have a white bead that's next. So for the white bead, it's the white dwarf. So the white is the white hot core. So what you see again here is another planetary nebula, but this is the Ring Nebula. It looks really similar to the Helix Nebula from earlier. But if we take a close look at the center there, there's a little white dot. That white dot is the white dwarf. It's the leftover hot core of that star. That's kind of like, that was like the sun. It is 100,000 Kelvin, which is about 17 times hotter than the surface of the sun is now. So this is pretty darn hot. It's so hot, it glows white here. All right, so that's the sun-like cycle. Now, all that material that comes off in the planetary nebula, it goes out into space, but that's gas and dust. And guess what? Maybe over here, there's a gas cloud, and it starts to condense by gravity, and it could form a star-forming nebula where it can form new stars. And that's the cycle there for a sun-like star. Now, for a massive star, everything is very similar up to that red supergiant phase. But what happens next is that these are so massive that they can explode because of what happens in the core here. So we have P for purple, and this stands for powerful explosion. There are some of the most powerful explosions in the entire universe. And what you see on the left is the remnant left behind by one of these supernova remnants that was seen in 1054 AD. And this is the Crab Nebula. And it's kind of like the guts of the star out in space, but that's all gas and dust. And on the right here, it's just a simulation of what it might look like when the star goes boom, supernova. So this is a powerful explosion that only happens with massive stars. Now, you might ask, what's left behind after the power explosion? Well, it really depends on what happens in that core region. So the very last bead here on your bracelet is black, which stands for black hole or neutron star. So massive stars can leave behind one of these two things. The more massive the star, the more likely it's going to leave behind a black hole. Robin from Texas and Amar from Ontario and Chloe from California and Lillian from Pennsylvania asks, can you tell us more about black holes, how they're formed, what they do, and what happens inside? Okay, well, black holes are black because they don't emit light. So that makes it really challenging for us to look for them if they create light, because they don't, okay? But if there's stuff around it, we can detect the things around it. So for example, starlight can bend around it, It can make things behind it look different. So astronomers can use that trick. That's really hard, but we can do it. But actually, the best way to find a black hole is when it's with a friend in a binary star system. And so this image here is of a black hole that's at the center. That little black circle is supposed to be the event horizon. But it's pulling material over from that other star, and that swirls around in this disk that gets really hot. It's so hot, it emits X-rays. We can detect the X-rays. And sometimes it launches these jets, like 2 garden hoses coming out. We can detect those too. So that's how we detect them and know that they're there. Now, what happens inside? I don't know. It's really hard to know what happens inside. We have to get information out of there. And if it doesn't emit anything, we can't say anything about what happens inside. And that's actually something that scientists want to learn about, is what happens in that moment when everything collapses down into a black hole. Maybe you'll be the scientist to help figure it out. Now, a neutron star is actually something that does emit light. It's very dense. It's about the size of a small city. It's really, really small, but it can be very massive, like 3 times more massive than the sun. And it's so small and so dense, it has really strong gravity, and it emits X-rays because it's really, really hot. So this is about 7 times hotter than that white dwarf that I was telling you about. So pretty cool. These are exotic objects for sure. So let's just recap here. So we have the sun-like star cycle, and we have a green bead for gas clouds that form stars. Then we have a blue bead for building the stars up to become their baby stars. Then we have yellow, yay, I'm a star. And then we have red, the ridiculously large giant. And then we have orange when the outer layers get sloughed off and become a planetary nebula. And then we have white when the white dwarf and it looks like a white hot core. And then we have massive stars like Spica. Okay, so the first 4 are exactly the same. Green means gas clouds. B means building up to become a star. Yellow, yay, I'm a star. Red, ridiculously large, like larger than the sun when it becomes a red giant. Then we have purple, powerful explosions. And then black could be a black hole or neutron star. So is that fun? Now you can look at the colors and you can tell all your friends and family about how you learned about the life cycle, and all the colors represent something here. Now, the sun is going to live in that cycle for about 10 billion years. And many of you already knew that the sun will live for about that long. Now, massive stars like Spica live for shorter periods of time. Because they're more massive, they can create more energy, and they can use up that energy, create that energy very, very quickly. And so they can live for only hundreds of millions of years, much, much shorter than stars like the sun. All right. So I hope you learned a lot about the life cycle here. And now I'm going to move on to the next section, which is doing some more fun demos here. I may go a little quickly, but you can always watch the recording later on here. Now, your eyes can see visible light. So if you're looking at the trees outside, I have a nice bank of trees here. I see that because something that is reflecting visible light is going into my eye. Or maybe you've seen fireworks. The fireworks are creating light that you see. The beautiful colored flowers are reflecting light from that you can see, or your pets around the house here. So visible light here are the different colors in the rainbow that you're used to. Now, in the chat, why don't you tell me, are there other kinds of light we can't see? So I'm going to look over my chat here. Actually, Jennifer, if you want, you can also call on a couple people.
Does anyone on the screen want to answer? I see Heidi. I'm going to unmute Heidi.
Hi, there's a few things. There are other kinds of light we can't see.
Can you tell us one?
I do not know.
Okay.
But I also wanted to say that the reason we see light is because, so say, I don't know, if you're looking at something yellow, it's hard to explain, but it's reflecting every color except yellow. And that's why we see yellow.
Very great explanation. I totally agree with you.
Thanks,
All right.
Heidi.
Thank you.
Do we want to take another question, another answer? Or do
Yep,
we
one more
wanna-
answer.
Okay, perfect. I'm gonna go to Penelope. I'm gonna unmute you, Penelope.
See if I can see here.
Penelope,
like-
what?
Yeah, go ahead, Penelope. I can hear you.
Good. So, sunlight we can't see because sunlight actually makes all the colors.
It does
The
make
rain-
the different colors in the rainbow. All right, let me
Thanks,
see. I'm gonna
Penelope.
take, yeah, thank you. I'm gonna look at the chat and see what other kinds of light we can't see. I see infrared light, ultraviolet light. I saw X-ray light. Okay, these are types of light. You are absolutely right. So let me, oh, I lost my cursor again.
And if
Okay.
you had that in mind, but we didn't pick you, you can give us a thumbs up to say that's what my answer was.
Nice. Right, the visible light is just a really small part of the electromagnetic spectrum of light. That includes ultraviolet light, X-ray light, gamma ray light, and then also includes infrared light. Now, you might not have known this, but microwave light is a type of light. You can't see it though. Radio is also a kind of light. You can't see it, but it's light. And they all have different kinds of energies. And guess what? Astronomers look at the universe and all these kinds of light. So what we're going to do now here, I'm just taking a time check here. Okay, Jennifer, I'm just going to really do this a little quickly more than normal because I'm looking at the time. So it's 20 of. So we're going to learn about the power of infrared light, which is redder than red that your eyes cannot see. So this demonstration here is, I'm going to have you guys, do one finger if you think that's the option, 2 fingers, or 3 if I ask you to guess. And I'll try to look at people in the gallery view here. So I'm going to turn off the stop sharing here. Okay, stop share. Okay, and then I'm going to move my view over here and pin myself so I can see what I'm doing. Okay, so the first thing I want you to do is I have these 3 cups. Now I'm gonna try to hold it up. There's water in there, okay? This is cup number 1. I have another cup. It is filled with water. There you go. This cup is filled with water. Now, I touched them, but you cannot. So you guys are astronomers and these cups are far away from you. Which cup is the hottest? Which cup has the hottest water in it? Okay, on the count of 3, hold up your fingers. Do you think it's cup 1, cup 2, or cup 3? All right, so on the count of 3, 1, 2, 3, put up your fingers. Which cup do you think is the hottest? I see 1s, I see 2s, I see 3s. Okay, I see pretty much all over the place, right? Because it's really hard to tell. 1, you can't even see the water in there anymore and you can't touch it. So what does that mean for us? Well, it means that we need some kind of special light to look at it. So let's take a look. So behind my screen here is a view of the infrared camera that's pointing right at those cups. So let's see if you were right. Okay, ready? 1, 2, 3. Oh my. Okay, so we see that the cups look different, okay? So this cup over here is glowing really brightly. This cup is not glowing as bright as the one next to it. And this one is kind of a blue color. So these are telling us which one's warmer. Which one do you think is warmer? The blue one or the red one? Okay, so which one's hot? So put up your fingers. Which cup has the warm water in it? 1, because it's glowing in the infrared. So I was able to see it using an infrared camera, but you guys could not see it with just your eyes, right? So infrared light tells us things that we can't see, but we can explore in a different way. Okay, so now I want you to Okay, so Jennifer, this is what I'm going to hide this again. Now, I'm only going to put one cup in front, okay? And then I want you to guess which one I put in. So Jennifer, I'm going to block myself here, okay? You tell me if I'm good.
when I can't see.
Okay.
Okay, I cannot see the cups.
Okay.
Can anyone out there, can you guys see the cups? No, okay, we all can't see the cups.
Okay. Can't see the cups. All right, perfect. All right. I have a screen. Now, it's the same set of cups. Cups 1, 2, and 3. Which cup do you think I put in the front? 1, 2, or 3? Go ahead, put your hands up in guesses. In 1, 2, and 3. Which cup did I put in the front? Can you tell? I'm seeing a whole bunch of different fingers too. All right, let me see if I can do this. Now, I can see, okay. Now let's see if you can see. Now we can't see with visible, right? But let's see if infrared, I'm doing this. Okay. All right. So notice I have cup 2 in front, but you couldn't tell when the trash bag was in front, right? With your visible eyes. But notice that even through the trash bag, the infrared camera can see that the in-between color, which was cup number 2, is in the front. So infrared light can not only see what is warmer, it can see through things like this trash bag, right? That's pretty cool. So it senses heat and it can see through things. That's really, really powerful for astronomers. Now let's see if I had another demo. Oh, okay. So you think that you can see through things. So I think you can see me through this, right? How many people think you can see through it if I put it in front of the cups? All right, let's test. Ready? Okay, put it up here. Ready? It can't see through plastic. That's different, right? So I see that some of you are putting on your infrared eyes. Put on your glasses if you've made them, because you can see with infrared, and that's what the Webb Space Telescope is going to do. It has infrared eyes. So if you have infrared eyes, you can see the temperature of things. You could see through things, but sometimes you can't see through everything. And this plastic tube is an example. But if I make this warm, hair dryer. Notice it's heating it up really hot. Before you couldn't see through it. Now we're actually seeing it glow because it's hot. So imagine if there's warm dust in space and an infrared telescope is looking at it, it might actually see the warm material glowing. Okay, so that's really, really, really cool, right? Whoops, sorry, tech difficulties again. All right, and then I'm going to show you one other cool thing. Now, if I put my hand up on the screen here, actually, I'll just do it in real time. So I'm going to warm up my hands. I'm going to sign this wall with my hands. Ta-da! So I left my handprint on there. So it's pretty cool that your hands can leave an imprint on the wall that you can't see with your visible eyes. But if you happen to have an infrared camera, it can pick it up. So that's pretty cool. All right, I'm going to share my screen again. So let's do a little bit more fun things here. Okay, share screen. And Jennifer, if you can just confirm it's the single slide.
Yep, it's looking good.
Great. Okay, was that fun? Do you guys like that? Do you see the power of the infrared? Okay, so let's look at these animals and we'll just do the top 3 here. So let's pick a volunteer, 3 volunteers, and let's pick the first volunteer, and I'm going to ask you to tell me what animal we're looking at in panel A. So these are infrared images of animals. Can you tell me what animal that is? So go ahead, Jennifer.
Okay, so I'm going to unmute Philip. Philip, you've been pretty keen all class, so. Philip, can you unmute yourself? Yeah, we can hear you now, I think. Hi, Philip.
So what am I supposed to do?
What animal do you see right here?
Looks like some kind of raptor.
Okay, kind of bird, yeah. It is actually, I think it is definitely a bird. I can't remember what bird it is. I was told it's a parrot, but that's kind of big for a parrot, but I'll take bird. That's great. Okay, second volunteer.
Okay, so I'm going to scroll down a bit. We're going to give some people who haven't answered us yet. I'm going to go to Jeremy. I'm going to ask you to unmute yourself, Jeremy. And we're looking for what kind of animal is in panel B.
It looks like a turtle.
Good job. It's definitely a turtle. And look, it looks a little bit warmer than its surroundings. So this infrared light tells us a lot of things. And let's say our third volunteer, let's guess D for the third volunteer.
Okay, D. Okay, I'm looking for a volunteer. I'm going to go with Madeline.
Okay. So D is a giraffe.
Excellent.
It looks pretty like cool compared to the horn.
Yeah, it is very neat. The infrared here, our bodies glow in the infrared. So
Yeah.
I wasn't able to show you my hand, but I think you saw me go in front of the screen sometimes. So your bodies give off light. Did you know that? Infrared light. Excellent. Okay, I'm going to pass by this for now. So what is infrared light? Infrared light is like heat. Our eyes can't see it, but we can see through it, like I showed you with the trash bag here. Now, we can't see visible light through it, but the infrared camera can see not only through it, the trash bag, but also sees the heat of the hand there. And so if there's dust, fog, or smoke, we can see through that. So the James Webb Space Telescope is an infrared telescope. It sees the part of the electromagnetic spectrum that your eyes cannot see, just like that infrared camera could do. Now, many of you might be familiar with the Hubble Space Telescope. Now, Webb is not replacing Hubble. They are friends in the sky. They will complement each other and be able to use the visible view and look at the infrared view, just like it gave us different information depending on what kind of light we saw it in, whether you had your Webb infrared eyes on, or if you just used your regular eyes here, it gave us different views and different information. So Jonathan from California asked, how does the new telescope compare to the Hubble Space Telescope? Well, the Hubble Space Telescope is about the size of a school bus. The whole observatory of the James Webb Space Telescope is about the size of a tennis court. Their mirror sizes are different. Webb's mirror here is 6.6 meters, while the Hubble mirror is 2.4 meters. And that person is there for scale here. So these are, they're not small things, but they're pretty big, right? And we have to put them in space. And here's a set of scientists and engineers at the NASA Goddard headquarters here with a full-size replica model of the James Webb Space Telescope. Now here it is in a facility where they're looking at all the mirrors and getting it ready so that it can be launched. But it's a giant telescope and it's heavy. So if you want to launch something big and heavy, you better have a really big rocket. So it's going to be launched on an Ariane 5 rocket later this year. Okay, so it also has to fit at the top. So there's a reason why Webb here folds up so it can fit inside there. But that also means that when we get it out into space, we're going to have to also figure out how to unfold it. And this is why some really brilliant engineers and scientists have been working on this for a long time. So after the Hubble space, after the Webb mission goes into space, the first few hours here, it's going to open up its solar arrays so it can get some power. And then it's going to fire its thrusters so it can move out to an orbit that's going to be beyond the orbit of the moon. Now, the first week, it's going to start to unfold. Now, the sun is hot. It emits infrared light. We don't want Webb to be seeing any light from the sun. So it has a sun shield that will protect it and keep it cool. Because remember, I'm warm and I can be detected in infrared light. So if an instrument is hot, it can't be detected either. So it has to cool off. So the sun shield helps it stay cool. And all the instruments need to be cool as well. So all of this is happening within the first week after Webb launches. And then the mirror has to unfold. So it's really slow process. So I want you guys all to be patient when this actually happens. And within the first month after it launches, scientists and engineers are going to be taking a close look to make sure it's doing everything it needs to be doing to get ready to open up its eyes and look at the universe in the infrared. Now, this is going to happen sometime later this year. All right, it's going to reveal amazing new things. We can look at young stars that are buried inside those dense regions. We can look at stars and spiral arms. We can look for planets and their atmospheres. So this Eagle Nebula here, if we move from the visible into the near infrared, we can start to see through it and start to see the young stars that are inside and then see the dust glowing. This is what we hope to do even better with Webb. And the same thing goes for the Planetary Nebula phase. Did you know that those outer layers create a lot of dust and it shows up in the infrared? So these are all really great interactive sliders through interactives called View Space. So we'll be giving you out some resources after this, and you can explore View Space interactives. It's free for anybody to use. It's part of NASA's Universe of Learning. So galaxies will study more. So together, we're going to explore the cosmos with Webb. We're going to look at the life cycle of stars, similar to what you just learned today. We'll look at other worlds and planets around all those stars. We'll look at galaxies and how they change over time. And then we're going to start to look for the baby galaxies in the early universe. It's so exciting. I can't wait. So follow us and learn more about the James Webb Space Telescope. Our telescope is a virtual starship. We're here, we let the light, all kinds of light, get detected by our telescopes so we can study the universe in a different way. Thank you.
Okay, so what I'm going to do now is I'm going to ask you a very important question that we got in the registration, and then we'll take a couple of kid questions from the audience, and then we're going to get into our Loop Lab prize. So I want to see a thumbs up if you think that Dr. Hart's job is extra cool. I think it's extra cool, and we learned so many cool things. So we have Cameron in Great Britain wanting to know what got you into space and how did you study to have it be your career?
That's a great question. So I was probably very little, like you all, looking outside my window in the summertime. And I saw this one star that I love to look at every summer. And I just stare at it and wonder about it. And that was probably the first time I knew that I really liked the universe and the stars, because I had no idea. Turns out that I actually wasn't even looking at a star. I was looking at Jupiter. But it doesn't matter. I got inspired. And by high school, I knew I wanted to study astronomy. I knew that I wanted to share my love and passion for the universe with other people. And so I've been really doing astronomy, education, and outreach my entire life. And it's a pretty darn cool job, I have to say.
Okay, so I'm going to take an audience question now. So if you have a question for Dr. Hart about anything you learned today or something you had in your head that you wanted to ask. So I'm going to go to Andrew. So I'm going to spotlight you, Andrew, and I'm going to ask you to unmute yourself, and you can go ahead and ask your question. Hi, Andrew.
Hi. What subjects do you need to study to be an astrophysicist?
That's a great question. Well, I really like, even before I knew I wanted to be an astrophysicist, I liked math. I like science. I liked art. I liked coding. How many of you like coding? I like being around other people. I like writing. And guess what? All of those things are pretty important things that I need to use now in my life. But I would say really keep up with your science interests, stay motivated, and just learn every day. I don't know everything, and I learn every day. So it's not something that's going to stop as you grow up. So keep up with all the things you're learning in school, because all of them are important at some time in your life, including when you become an astrophysicist.
Thanks, Andrew. Okay, so I'm going to look out for another raised hand. I'll see if maybe we can take 2 more if we get a really quick question. I'm going to go to Rhea and Gia. I'm going to add your spotlight and I'm going to ask you to unmute yourself. Hello.
Hi. So how big is the James Webb telescope again? Like how long is it? You said 6 point something.
Oh, so the main mirror, which looks like this hexagon that you see here, is about 6.4. Let me just look at my notes real fast. I don't have always the information at the tip of my tongue. 6.6 meters. So this is about a meter thick. So think of 6 2/3 of those wide. Okay. Now the Hubble Space Telescope is 2.4 meters. So 2.5 of these. So they're definitely different in size, and that helps astronomers collect some of the faintest light from some of the youngest galaxies that we can see far, far away. So the bigger the light bucket to look at the light, the fainter the things you can see.
So it's only that little hexagon with 6.6 meters?
The whole thing, the whole hexagon. So there's a whole bunch of smaller hexagons. They're about a meter in size. So it's a segmented mirror. So it's composed of many little mirrors to make one giant mirror.
Wow.
Great question. Thank you. Okay, I'm going to push my limits and take 1 more question and then we'll get into the prize draw. Okay, I'm looking for someone with a raised hand, someone who we haven't heard from before. I'm going to go to Annabelle. I'm going to put your spotlight on.
Hi, Annabelle.
My name's actually Ethan. So, do you know what dark matter is? I've heard of it, but I'm not sure.
You might have to get closer to your, oh, the camera went off. I don't think we can hear you, so I'm just going to quickly go to another question, but I hope you can find the answer to your question somewhere. I'm going to remove the spotlight and I'm going to quickly go to 1 more. Okay, I'm going to go to Blaze Ferguson.
What happens when a star dies? Does it like turn into a black hole?
It depends on how much mass there was when it was, yay, I'm a star sage. So if you're like the sun, you're never going to turn into a black hole. You're going to leave behind a white dwarf that basically is hot. It's like a giant ball of carbon in space that's hot and it's just cooling off.
I thought it was just like a big explosion, then there was a big black hole.
Well, not for the sun. For stars that are 10 times, 50 times more massive than the sun, it will probably go have the powerful explosion and become a supernova. And then it could leave behind a black hole or a neutron star. It really depends on how crushed that core gets. So sometimes it doesn't crush enough and it becomes a neutron star. But if gravity wins, it's going to turn into a black hole.
Okay.
Yep. So it depends how much mass it is when it's an adult star.
Okay.
Thank you for your question. Okay, so now we're going to keep Dr. Hart on the line just to say goodbye. But before we do that, I'm going to do my Loop Lab prize draw. So we have our bag here with everybody's names in it. Disappearing. I'm going to shake it up, make sure it's fair. And if my mad scientist helper can put up on the screen what our Loop Lab subscription box looks like, you can all see what you're potentially going to win. So Loop Labs is the Mad Science STEM subscription box with 6 amazing boxes available. So the winners of this draw will each receive our Gross Science box. Who doesn't love gross science? Where you can make a foaming fountain, a DIY ooze ball, and ghost goo. Yeah, but awesome. So you can head to shop. Sorry, I'm forgetting the address. Shop.madscience.com. I'll repeat that again. Shop.madscience.com. You can take a look at all of the cool boxes we have. We have 6 available right now. So the first winner is Brian A. Congrats, Brian A. Everyone clap for Brian A. The next winner, we have 4 prizes to give away. Everyone do a drum roll. You can see if you guys are doing a drum roll, so hopefully you are. The next winner is Scarlet T. Congrats, Scarlet T. Okay, we have 2 more. You still have a chance. Drum roll, please. The winner is Callista W. Congrats, Callista W. Okay, there's 1 more left. Everybody, fingers crossed that it's your name. The winner is Ranjani K. Congrats, Ranjani K. So if you didn't win, that's okay. There will be other events and other prizes to be given away. We want to thank you so much for joining us. I'm going to throw it back to Dr. Hart so she can say goodbye, and then we'll have a special opportunity for you all to say hi and bye with your glasses on later.
Yes, thank you so much. This was so much fun for me. I really hope that you know and share out what you learned about life cycle stars and get super excited for the launch of the James Webb Space Telescope this year. So look around in your community. There's probably going to be a launch celebration event going around somewhere. And if not, you can host your own. You can even make star life cycle necklaces or bracelets with your friends and family and have your own party to celebrate this wonderful new telescope that's going to reveal the universe in ways that we can't even imagine. So thank you.
Thank you so much, Dr. Hart. This is an amazing experience. We learned so much. Thank you all out there for joining us and for your questions. We hope to see you again. If you want to share your pictures of your bracelet, of your glasses, you can head to our social media pages. You can tag us at Mad Science Group on Facebook or Instagram. We hope to see you there. Like Dr. Hart said, we'll be sending out a resource package. So you can take a look at our bracelet instruction booklet. It has tons of extra cool facts about the Webb Space Telescope. It has links that you can go to NASA websites and you can keep the learning going. And we want to say thank you again to the National Institute of Aerospace and to Goddard for working with us to bring this event to you. And now I'm going to do an extra special. Everyone's been muted and you guys have been really kind, but I'm going to unmute everyone and say bye. So if you guys want to all say hi and bye and thank you, Dr. Hart, and you can put your glasses on and we'll spotlight a few kids on the way out. So I'm just going to unmute everyone. I just have to do it. Look where it is. So, okay, so I'm turning off the unmute button so everyone can unmute themselves. In 3, 2, 1, and say bye. Thank you, Dr.